but his was sound, and he found that the coefficient was, he basically made some hand-waving arguments, said it was order 1, and it was like 1.2, so he basically got it correct. Yeah, they actually came around to arrest him at his house in England, because he had worked on the bomb, and he actually worked at Los Alamos. But so you then basically you look at the plot of r versus time. Say so on a log it's going to look like this, with a slope of 2/5. And basically from the intercept, you get the coefficient. You get the coefficient. So he's saying this is 1, and then the coefficient gives you this, and you know what this is. Okay? But scaling arguments are sort of a black magic. But it's actually the best thing to do is to pose the problem formally. Usually, depending on what stage of one's career one is in, one approaches things differently. But when I was young, I used to try and I'd solve the problem, and I'd figure it all out analytically, and then at the end, I'd try and come up with a simple scaling argument to rationalize my result. But as you get older and more lazy, you go straight to the scaling argument. But it's very frustrating, and you should do both, because sometimes scaling arguments, you can get it wrong. And I work with some excellent French physicists, and they always start and end with the scaling arguments, which can be rather frustrating. But I think it's nice to sort of combine they have very good insight, very good physical insight. And it sort of relies on physical insight, the ability to do scaling, but it's sometimes nice to back it up as well. Okay, so we had this concept of surface tension, and so the dimensionless groups that come up when you're looking at interfacial problems. The lighting's not great in here. Can we kill those lights? I should mention another. Thanks. So we've seen surface tension is a force per unit length. This actually is the simplest way to measure the surface tension of an interface is a plate tensiometer. So let me just mention this. So basically, if we have a long plate, and we dip it into an interface, and then we extract it, then the maximum force that you're going to get from the surface tension is 2 sigma times the length of the plate. So this is L. So as you withdraw, basically what will happen is the thing will get stuck on the corners, and then you'll have this. Sorry, I should be in the opposite direction. You have then a force which is 2 sigma L. So the longer the plate, the larger the force, and the less accurate your system has to be. But this basically gives you the simplest way to measure surface tension. Okay? And so you can, basically, ring tensiometers are based on the same idea. You basically extract something across an interface, and you measure the force acting on it. Okay, so these are. Okay, so. Yeah, right. So we were looking at dimensionless groups arising in interfacial flows, and so they're always these dimensionless groups are all. You can think of them as they're basically ratios of either forces or pressures or energies. So the first term you can think of as rho as a dynamic pressure over a curvature pressure. So rho u squared over sigma over a. This is a viscous stress to a curvature pressure, and this is hydrostatic to curvature pressures. And we saw, basically, we're going to refine this picture today, but if you put a blob of fluid on a surface, it's going to spread under the influence of gravity, and it's going to be resisted by surface tension, and gravity will win generally when the blob is large. And by large, we say large relative to the capillary length. Okay, so now here's your next scaling. Did you guys work through this? So this is what sets the size of raindrops, which is definitely a problem that anyone who takes this course has to know how to solve. Okay, so it's actually not that obvious. But, and so you have a couple of steps. So first you have to calculate the fall speed, because the fall speed is going to set the dynamic pressure, which is going to cause drop rupture, right? So you get the fall speed simply by balancing the aerodynamic drag with the weight of the drop. Okay, so the aerodynamic drag depends on the density of the air. The weight of the drop depends on the water density. So we have the aerodynamic drag on the left, so that's rho u squared a squared. And then we have the weight of the drop. Okay? So that gives us the fall speed, which goes like square root of GA. And we have the ratio of the densities in there necessarily. Okay? But the fall speed goes as square root of GA, A being the characteristic size of the drop. Okay? So, so what happens, so we can actually rationalize the first distortion of a drop. So what does your intuition tell you that a raindrop looks like, by the way? Artists always get this wrong. Artists always do this, right? It's sphere to leading order, but to second order. Okay, so this is wrong. So this is the shape of an air bubble moving in non-Newtonian fluid, as it turns out, and of course tears. But that's a raindrop rolling down a window pane, right? But what's the first distortion to a sphere? So let's think about it. What's that? Ellipse, right? Oblate or prolate? Is it like that or is it like that? Long? You guys went for prolate? What? Yeah, multiple choice. A is this. B is this. Okay. Okay. Okay, ready? So let's think about this. We have flow streaming past a sphere, and we want to get the first distortion, right? We know that the pressure is highest inside the drop, right? And it's constant, but we know that the air pressure is varying as we go around the drop owing to Bernoulli pressures, right? So we know that P plus 1/2 rho u squared is equal to constant, okay? So here we have a stagnation point. So the air pressure there is going to be what? Maximum, right? So let's call that P plus. And here we have high pressure, low speed, and here we have high speed, low pressure. Okay, so let's call that P minus, okay? But the highest pressure in the system is always inside the drop. But what this is telling us is that the pressure difference across the interface is smaller here than here. So how can that be? How can we have that? We can have that because we know that the pressure jump is the product of the surface tension times the curvature. Okay? So because the pressure difference is smaller here means that the curvature is smaller. Okay? So the first distortion of a drop is into a oblate ellipsoid. Okay? Okay, you got that? Okay, and so the point is you have this stagnation pressure, and this stagnation pressure will actually cause the thing to rupture if it's too big. And that's what you see here. So here, these are experiments done by David QUÉRÉ, and so at the Collège de France, which is, I think, a 6-story building, he took a bucket of water and he threw it off, and he had high-speed video cameras going at every floor. And so this was on floor number 3, I think. But you can see the stagnation point actually ultimately leads to this thing spreading and then going like this and then into a thin sheet, basically into a parachute. Okay? And that parachute then breaks up, so it eventually shatters. Okay, and so the question is, so when can we have this picture? When we have an oblate, nearly spherical raindrop. So in order to avoid this, the curvature pressures, so I say drop integrity, that is to say, in order for surface tension to keep the thing from breaking up, then the curvature pressure has to be larger than the characteristic dynamic pressure, which is causing raindrop cleavage, right? And we can see that this characteristic pressure, we can get that in terms of G simply by using the force balance, right? Because we have U, we've expressed U there in terms of G, so we see this, okay? So again, the constraint, the requirement for dynamic stability is that this be less than this, right? Surface tension, again, wants to keep things spherical. We have these aerodynamic pressures which are trying to cleave the drop in two. So this has to be less than this. But from the force balance, we can express this like this. So we see then that what comes out is a simple result that the drop has to be small relative to the capillary length. But it's not obvious because you have this intermediate dynamic step, right? You have to get the characteristic dynamic pressures which cause cleavage from the force balance. Okay? A is the size of the drop. Yeah. Okay, so again, so I always say, surface tension is important relative to gravity when you're small relative to a raindrop, and this is why, because it's this balance between the two that sets the size of a raindrop and ensures that they be on the millimetric scale. And it is a very interesting question, what would happen if surface tension, I've always wanted to give this as maybe I should just give this as a possible alternative to homework, is an essay question on how different the world would be if the surface tension were 100 times higher. Right? We'd have huge raindrops to begin with. It'd be very dangerous to go out. We'd probably all be covered in water-repellent skin. But there are all sorts of interesting questions, dynamical issues that would come up. So that's the size of raindrops. So you can all do that now, right? Any questions? So you're asking about this requirement? Yeah. So again, you have this picture here, the stagnation pressure causing, so you have these dynamic pressures around which basically want to break the drop up, right? But these are being resisted by the curvature pressures, right, which simply want to keep things spherical. Okay? So the question is, when can one dominate the other? Right? And when they're very small, the curvature pressure will win. Oh, really? Plateau, you mean? The pinch off? Yeah, so, yeah, it is. All of these systems are trying to minimize surface energy. That's certainly what causes a thread to pinch off, right? Here, that certainly during the fracture stage, like when this big thing, it's in a very energetically unstable state there when it's a big balloon, right? Because what it wants to do is to break up into small drops, right? And so, yeah, in some sense, all of these systems are being driven by a desire to minimize the energy of the system, in particular the surface energy. So long threads, sheets are all energetically unfavorable. But you see here in this case, it's more complicated because you also have dynamic pressures around, right? So you're not simply minimizing the surface energy. You also have kinetic energy and so forth. Okay, so a nice question that we can get at without yet doing any math is puddles. Okay, so what sets the size of puddles? So I've just made this argument of putting a blob of fluid onto a surface, and we saw that it would spread to some distance. But there are all sorts of, let me show you the various possibilities. Okay, so here are 3 different blobs. And we know intuitively the higher the surface tension, the more the thing wants to be spherical, right? But we're seeing, so these are the surface tensions. So this is water's around 70. This is, I think, an oil, and this is mercury. So you can see basically the tendency to be spherical is determined by the amplitude of the, whoa, hold on here. By the amplitude of the surface tension, but there are also wetting effects. So it actually also depends on the chemistry of the interface. So I just want to show you the many things that can happen. This I can't seem to do in this mode. Let me just unplug for a second. Okay, so in addition to the magnitude of the surface tension, there's going to be something called a contact angle, which is going to come in. And the contact angle depends on all 3 of the surface energies. So we've defined the surface tension, so that's the force per unit length or energy per unit area of this interface. There's also energy per unit area on this interface and on this interface. And all 3 combine to define the contact angle. And you can see that not only is the curvature different in these systems, but the contact angle is different. Okay? So we want to try and understand this. So here again, one can see, oh boy, that doesn't help. I have to keep getting out of this. This was not designed for Macs. Okay, so here, 3 different possibilities. So different contact angles. The oil goes basically flat, fluorinated oil, and then we see the surface tension increasing, the contact angle increasing progressively. The contact angle is this angle. So the angle made from the inner surface to the tangent of the drop. Okay. So here's a case where you put the drop down, it just spreads in a very thin layer, so the fluid wants to be on the solid. It's energetically favorable to wet the solid. And typically the extent of wetting, so the extent to which this thing spreads, will depend on how clean the surface is and also the chemistry of the surface. So here, water on glass, we saw a nice drop with a well-defined contact angle. Now we're going to clean it. And the thing spreads much more readily. Okay? So it turns out that there's an impediment to contact line motion, which associated with roughness on the surface. So you have a rough or a dirty surface, and the thing gets stuck as it tries moving. So here we see water on silicone. So he basically puts down a drop of silicone, coats the whole surface with silicone oil, and there you can see, oh, you can't even barely see there, can you? In any case, it's a very well-defined drop with no, which doesn't spread at all. Let's hope the next ones look a little better. Okay, so there's a partially wetting drop. That one's pretty clear. And again, so this is water on different surfaces, glass, plexiglass, and wax. And you can see the difference, the different contact angles. Okay. So we want to understand how we rationalize these things. And these things are very important on a small scale, both technology and biology. Okay. So here, and we want to be able to rationalize the shapes. Okay. So what sets the size of a puddle? If you tell me the volume of a puddle, looks like these guys have a maximum depth, and we're going to see that in a moment. And then there are more interesting things. So here we have a surface which has a chemical treatment. Okay, and so we can see here that the contact angle is higher for this drop than this drop. Okay, so basically the surface energy of the substrate is changing. So we have a chemical gradient. That being the case, you can you can actually propel droplets. Okay, so here we put down a drop, and it prefers to be on one side than the other, so it actually moves spontaneously. And so this is a way for moving drops around on a solid surface. Yeah, you can have, yeah. In fact, you can also, something called liquid pearls, you can coat with the lycopodium powder, and then they never wet. So you can have situations. And you can also, you can vaporize drops. So if you put a water drop on a hot plate, then it will evaporate on contact. And so you have an air layer beneath it, and then it will simply roll. Okay, so these are all basically variants on the same theme, which is fluid puddles, and so we're going to look at these now and try and rationalize. Oh, here's a slightly more exciting version of it. Has anyone ever seen one of these? The Brazilian pygmy gecko. The Brazilian, so this is a lizard, which is, I think it's in total 4 millimeters long. Mice. Hold on. I can't do anything on this side.
The Brazilian pygmy gecko could sit comfortably on a fingertip. It's so exceptionally small that no other reptiles compete with it.
This is rather losing the...
But it's so...
Yeah. Yeah, that's good. That's getting better. I don't think we need it. We don't need any of the lights, though. I mean, let's kill all of them. All, yeah, there we go. Still can't see it that well, eh?
It's so exceptionally small
Yeah, this is still rubbish. It's better here.
It's so small that it has special problems with, for example, rain. Drown in a drop, but its skin is hydrophobic.
So watch this. You'll see that drop?
Rain cannot wet it.
Right, so that's a very high contact angle. It's a rough, waxy surface. And so because of this, this is how it deals with rain. And when it goes in water, it never sinks despite the fact that it's heavier than water, simply because the energetic cost of submergence is so enormous because of its surface coating.
It's so light and its skin is so
It's not so light. Its skin is water repellent. They're usually pretty good. He got that one wrong, though, Attenborough.
Such miniaturization is certainly very impressive, but the reptile body can be transformed even more dramatically.
What's that? Yeah, well, it would have you ever seen, I'll show later in the class, you know, there's this ridiculous thing that was going around YouTube about these guys who were running on water. They said they were running on water. Did you ever see this? Yeah, it's total nonsense. But they said, we've got water repellent shoes. I'm like, Right. Oh, no, that's right. No, this was in Spain, this one, actually. Yeah, but again, different forces become important on different scales, and on a small scale, surface tension is important, wettability is important, so these very small creatures can benefit from having a water repellent surface. It's not going to help us at all, right? So I was consulted on that, and I said, stop wasting my time. But, so, it was actually kind of a cool video, though. And a few people bought it. So, okay, so this is what we're going to talk about now is wetting. And so the wetting of a solid by a fluid. So as we've seen that surface tension of an interface, a fluid-gas interface like air-water has an associated interfacial tension or energy per unit area. Same is true of the other surfaces. Okay. So the solid gas, a solid gas interface, a solid liquid interface all have energies per unit area. And the relative magnitudes of these sets the contact angle. So I'm going to first do, before we come to contact angles, I want to look at a relatively simple problem, which is puddles. Actually, I can probably finish up with this. Yeah, so we're going to finish up. So I'll derive this Young's relation. So this prescribes the equilibrium contact angle, theta E, which we see there. So again, this is that angle which is very large, for example, in the case of geckos. It's defined in terms of the three surface tensions in the problem. So that's the liquid gas, this is the solid liquid, and this is the solid gas. So those three energies combine to give you the equilibrium contact angle. And the easiest way to see that is that's simply the horizontal force balance at the contact line. So the contact line is the point of contact of the three phases. And that one can see, again, if we consider these are force per unit length, that's the horizontal component of the force balance. Okay, so I think I'm going to not need the, we're going to come back to this at the very end. So we're going to try and rationalize capillary adhesion used by these bugs. Okay, so I think I don't need that anymore. I'm going to just use the board now. So maybe if we can get the lights on and get rid of this. Can we do that? Let's take a break while we do that. How do we...